And here is the third structural design pattern from the Gang of Four design pattern book. This one is called Composite Pattern, and it is a pattern you use when you're creating a tree structure of components that can contain child components. I'll start with a quick summary of what we're trying to accomplish with this pattern. The composite pattern is a good choice when you are trying to accomplish the following. You need a tree structure to represent a part hierarchy. You want to compose objects out of one or more child objects. You want clients to treat individual objects and compositions of objects in exactly the same way. Let's go through these points. So, in this pattern, you are working with objects which, in the terminology of this pattern, are called components. And the key issue here is that some components actually contain one or more child components. And these child components can also contain child components, thus forming a tree of components. We have a special name for components with or without child components. Any component with at least one child component is called a composite, and any component with 0 children is called a leaf. The nice thing about this pattern is that it lets you treat composites and leaves in exactly the same way. Clients will only interact with the component interface, which offers no information if a given component has children or not. This fact is irrelevant to the client. The composite pattern offers a number of benefits. First of all, the pattern lets you set up a hierarchy of components. You use the pattern to declare components that can contain components that can contain components. This is perfect for tree-like data structures like folder hierarchies, organizational charts, tables of contents, and so on. But the pattern offers another advantage. The calling code doesn't need to know which components have children and which do not. All clients only interact with the component interface and are completely unaware if they're dealing with a composite or a leaf object. This effectively hides the complexity of the data structure from the outside world. The composite pattern is ideal if you are applying a sequence of operations on a tree-like data structure, and your calling code doesn't care if the operation gets applied to a composite or a leaf object. Here is the UML diagram of the composite pattern. At the top of the diagram is the abstract component class. It declares a very simple interface, which consists of a single method called doThis. Both the leaf and the composite class will implement this method in their own way. On the left is the leaf class. It represents a component without any child components. As a result, there is no need to implement additional methods for handling child objects. Instead, all the leaf class does is implement the single doThis method. On the right is the composite class, which represents a component with one or more child components. As a result, the class has some extra members for managing child components. First of all, there is a protected field member called Elements, which contains a list of all child components. There are also extra members for managing the collection of child objects. In the diagram, one of these members is shown, the addElement method. Finally, the class also implements the doThis method. But, contrary to the leaf class, the composite class applies the method to both itself and all child objects. A simple for each loop iterates over all elements and calls the doThis method on each child component. And this is the fundamental difference between a leaf and a composite object. A leaf will only apply the operation to itself, whereas a composite will apply the operation to itself and all of its children. To demonstrate the composite design pattern, I will show you an example. I am going to create a simple class library for rendering an HTML web page. I will implement classes for each HTML tag that I'll use in my example. I will implement the tags as either leaves or composites, depending on if the tag is allowed to have nested content or not. My component interface will have only one single method called render. This method returns the component in its HTML representation. The render method in a composite automatically calls the render method of any child objects to render the entire HTML subtree in a single go. I will implement the pattern with the following classes. Okay, let's take a look at the code. I will start with the HTML node class. You can see that it's a simple abstract class that sets up an abstract render method. All subclasses of HTML node will override this method to render themselves in the correct manner. The first subclass we'll look at is the leaf node. This represents a leaf node in an HTML document, so a node that does not have nested child nodes. You can see that there are no new members introduced here. The leaf node is simply an empty subclass of HTML node with no additional methods or fields. And here is the text class, the first non-abstract subclass of HTML node. This class represents a fragment of text in an HTML document. So here is a protected string field for holding the text. And here is a constructor for initializing the text field. The render method simply returns the contents of the text field. The class does not have child components, so there's nothing more to render. Okay, now let's move on to the composite branch of the object hierarchy. I'll start with the HTML tag class, which sets up an abstract interface for composites. You can see here that an HTML tag is an abstract subclass of the HTML node class, and it introduces several new members. First of all, there's a tag name field here that holds the HTML tag name to render. And here is a generic list of HTML nodes called elements that contains the collection of child components. Also note that this method here, called addChild, lets you add a new child component to the collection. And here is a protected constructor that lets you initialize the tag name. And here is the render method. The method not only renders itself, but also all of its children. This code starts with an opening tag, then collects all output from the child components, and then adds a closing tag to complete the HTML fragment. And here are the concrete subclasses of HTML tag. They are the HTML, body, and P class, and each class corresponds to the HTML tag of the same name. These subclasses simply provide a public parameterless constructor that initializes the tag name. Okay, I'll conclude with the main program method. The code here sets up a simple HTML document consisting of a nested HTML, body, and paragraph tag. And finally, it adds a nested text element inside the paragraph. Then the code calls the render method on the outermost HTML element, which will render the entire document, including all children. Let me run the program to prove to you that everything is working. I'm compiling the code now, and now I'm going to run it. Here we go. And there you have it. A very simple HTML document consisting of an outer HTML element, a nested body element, a nested paragraph element, and finally some text. Everything works. Okay, here is a quick checklist you can use to implement the composite pattern. First, identify all composite objects in your application that are composed of nested child components. Then create an abstract component base class that contains the lowest common denominator interface. The interface should only contain the API that needs to be applied uniformly across all objects. Then add a derived leaf class and add any leaf management methods to this class. Add a derived composite class and add child management methods to this class. Then implement the component API for the leaf and composite classes. And you can add as many subclasses of leaf and composite as you need. And here are some final comments. The most important fact you need to realize about this pattern is that it completely hides the fact that a component can contain child components. The differentiation of components into leaves and composites is completely invisible to the outside world. This is not a problem if the outside world only needs access to the component API. The subclasses can decide how to implement the API without having to expose any kind of child management interface to the outside world. However, sometimes you might need to iterate over each component in the hierarchy. With a pure composite pattern, this isn't possible, because information about the hierarchy is only contained in the composite objects and not in the components or the leaves. The only way to make this work is by adding a separate visitor or enumerator pattern. You sometimes see developers moving all child management code into the component class to avoid this problem. This provides instant enumeration and visitor support directly at the component level. If you do this, please keep in mind that this actually weakens the composite pattern, because now the leaf class will also inherit the complete child management API, and that code doesn't make any sense in the leaf class. Okay, so here's a summary of what we have learned. The composite pattern is a good choice when you want to compose objects out of one or more child objects. The pattern treats individual and composite objects in exactly the same way. The pattern is ideal if you are applying operations to a tree data structure, and the calling code doesn't care if the operations are applied to a composite or a leaf object. Composite objects can be enumerated with an enumerator or visitor pattern. Some people put the child management API in the component class. This provides instant enumeration support at all levels, but it also makes the pattern more brittle.